Welcome. Today, we're cracking open a detective story, one that plays out thousands of times a day inside medical labs all over the world. It's a super high-stakes investigation to unmask these tiny, microscopic culprits, and most importantly, find their weaknesses.
You've been there, right? You're feeling absolutely awful, you go to the doctor, they write a prescription, and a few days later, you start to feel human again. But that prescription, that's not just a lucky guess. It's actually the final clue in a serious piece of investigative work. So how do they know which antibiotic is the right one for the job?
So let's make this real. Here's our case file. We've got a 65-year-old man with pneumonia. All the signs are there. Fever, a bad cough, trouble breathing. The evidence points to a bacterial infection. But, that's kind of like saying a crime was committed somewhere in New York City. We know what happened, but we have no idea who did it. And finding that who is everything.
Okay, so where does any investigation start? Well, just like any good detective, the very first thing our lab team needs is evidence. You can't solve a crime without clues, right? And in the world of microbiology, that means getting a good, clean sample from the patient.
Now here's a bit of jargon for you, but it's a key one for this whole case. Etiology. It's really just the scientific way of saying the cause. The lab's entire mission, their whole purpose, is to pinpoint the specific etiological agent. That's the bad guy, the exact microbe making our patients sick.
To do that, our lab detectives have two main strategies. First, they can look for direct evidence. This is like finding the culprit red-handed. You're looking for the bacteria itself, or pieces of it, like its DNA fingerprints. The other path is looking for indirect evidence. This is more like finding signs of a struggle. You're searching for the body's own alarm bells, that immune response that it launches to fight off a specific invader.
All right, so a sample in our pneumonia case, maybe some sputum or blood, it arrives at the lab, the evidence is on the table. Now the classic detective work begins. It's time to see which suspects are going to show their faces.
And they do this with a process called a culture. It's brilliant, really. They take the sample and spread it onto the special nutrient-rich gel in a petri dish. It's basically the perfect buffet for bacteria. This lets any microbes in the sample grow and multiply until there are millions of them, enough to actually see. It's like a police lineup, but for germs. You're just waiting to see who's hiding in there.
So here's how it works, step by step. First, that sample is collected really carefully so nothing else gets in it. Then it gets spread onto that nutrient media. And finally, the dish goes into an incubator, which is just a warm, cozy box that helps the bacteria grow. After a day or two, bam, you get these visible clusters called colonies. Each one of those little dots is a potential suspect.
Okay, so we've got our suspect, we've grown it, we've identified it. Case closed, right? Not even close. Now comes the single most important part of the whole investigation, the interrogation. We have to find this culprit's weakness.
And this interrogation is done with a test called antibiotic susceptibility testing, or ABST for short. What the lab does is they take the bacteria they've just grown and they expose it to a whole panel of different antibiotics. This is how they figure out, with certainty, which drug is actually going to be effective inside the patient's body.
And the results of this test come back with one of two labels. If the bacteria is susceptible, that's the green light. It means the antibiotic works. It stops the bacteria in its tracks. But if it's labeled resistant, that's a huge red flag. It means the antibiotic does nothing. The bacteria just shrugs it off and keeps growing. This is the exact piece of intel the doctor needs to choose the right weapon. Now, growing a culture is great, but it can take a day, sometimes more. And in some cases, you just don't have that kind of time. You need answers and you need them fast. That's when the lab brings out the high-tech gadgets.
And these modern tools give them some amazing options. You've got antigen detection. Think of that like finding a piece of the culprit's uniform left behind at the crime scene. Then there's nucleic acid detection. This is the big one, like PCR tests. It's the equivalent of finding the culprit's DNA. It's incredibly specific. And finally, antibody detection. That goes back to the indirect route. It's like hearing the body's own security alarm going off, telling you who the intruder is.
So we've looked at the whole playbook, from the classic stakeout of a culture to the flashy high-tech DNA analysis. But why do we go through all this trouble? Well, because getting the right answer here is critical, not just for one patient, but for all of us. When these microbe detectives close a case, it has three huge impacts. First, and most obviously, it guides the doctor to prescribe the perfect treatment for that individual patient. Second,
It helps public health officials decide how to prevent that infection from spreading to other people. And third, all this information gets collected into a giant database that helps us track the rise of antibiotic resistance across the globe.
You know, at the end of the day, this entire complex process really boils down to one simple, powerful truth. You cannot pick the right weapon if you don't know who you're fighting. Getting the diagnosis right is what makes precise, effective treatment possible.
And that leaves us with one last and pretty urgent question. These tiny organisms, these bacteria, they are constantly changing, evolving, and learning how to outsmart our best drugs. So the real challenge for our microbe detectives isn't just solving today's case. It's about staying one step ahead in a biological arms race that never, ever ends. And the big question is, can we keep up?